The European Council for Nuclear Research, CERN, is making groundbreaking discoveries that it is trying to hide from society. Recently, they've unearthed findings so striking from the Large Hadron Collider, LHC, that they hint at the possibility of alien life in another dimension. This revelation has sparked a global conversation, with experts fiercely debating what it could mean for our understanding of the universe. Could this sensitive information indicate that we are on the verge of understanding phenomena that were once considered beyond our reach? Let's explore the darker, more shocking implications of what lies beyond. At the forefront of scientific exploration, the European Council for Nuclear Research, commonly known as CERN, stands out for its pioneering work in the realm of particle physics. This renowned research hub recently made a startling announcement from its famous Large Hadron Collider, revealing a discovery so unusual that it could radically alter our understanding of the universe. CERN researchers have stumbled upon findings suggesting the possible existence of alien life forms in a parallel dimension. This provocative idea has ignited a wave of excitement and sparked vigorous debates among scientific experts across the globe. CERN has been a hub of high-risk, high-reward experiments since it was founded in the mid-1950s. It has consistently been in the spotlight not only for its scientific breakthroughs, but also for stirring public outrage at potentially dangerous experiments that could create black holes, tear gaps in the fabric of reality, and pose other substantial risks. Among its most notable and debated achievements is the construction of the Large Hadron Collider, the world's largest and most powerful particle accelerator. Operational since September 10, 2008, the LHC is the latest major addition to CERN's complex of accelerators. It features a loop of superconducting magnets that extend over approximately 16 miles and a series of devices that boost the particles' energy levels as they hurtle around the loop. The construction of this colossal scientific instrument cost over $45 billion. However, many argue that the investment has paid off handsomely, as the LHC has led to some of the most important scientific discoveries of recent decades, including detecting the Higgs boson and numerous other particles previously unknown to science. The LHC at CERN is an enormous machine, a marvel of modern science capable of accelerating subatomic particles to speeds just shy of the speed of light. As these particles zoom around its 16-mile loop, they complete over 11,000 circuits each second, pushed to incredible velocities by a sequence of incredibly strong electromagnets. These magnets create a magnetic field inside the accelerator that is almost 1,000 times stronger than the natural magnetic field surrounding the Earth. There are concerns about the potential impacts of such a powerful magnetic field on the electronics nearby and the Earth's magnetic field itself. As particles within the LHC reach their peak speeds, nearly equal to the speed of light, they are directed to collide with each other head-on. This collision results in a spectacular burst of energy and a spray of new particles which scatter in all directions. Most of these particles exist only briefly, decaying within fractions of a second. By varying the types of particles that are made to collide, scientists can explore and discover previously unknown particles amid the chaotic aftermath of these collisions. To capture and analyze the results of these particle collisions, the LHC is equipped with highly sophisticated and sensitive detectors placed around the collision sites. These detectors gather vast amounts of data from each collision, precisely recording everything. The data collected is immense, accumulating rapidly and requiring extensive time and resources to sift through. Each year, the experiments at the LHC generate more than 15 petabytes of raw data. The LHC has developed extensive storage systems to manage and store this data. In 2017, a significant achievement was reached when more than 200 petabytes of data were permanently stored in the LHC's tape libraries. To put the volume of this data into context, consider that 1 petabyte alone is equivalent to about 250,000 movies. The sheer scale of data produced by the LHC is staggering, encapsulating a wealth of information that holds the keys to unlocking the mysteries of the universe. This data, when meticulously analyzed, allows researchers to peer deeper into the fabric of reality, testing the limits of our understanding of physics and the universe. In the vast sea of data collected by the LHC, scientists are meticulously searching for clues that could unravel new mysteries of the universe. One particular focus of their investigation is a unique type of subatomic particle known as a quark. Quarks are the very foundation of all matter, existing in several distinct types or flavors, as physicists like to call them. Each flavor of quark behaves differently, but they are all crucial for forming the protons and neutrons that make up the atoms in everything around us. Among these flavors, some are incredibly unstable, quickly transforming into other types of particles almost immediately after their creation. One such unstable quark is the beauty quark, known for its exceptionally short lifespan, lasting just 1 or 2 trillionths of a second. What caught the scientists' attention was an unusual pattern in how these beauty quarks decay. Typically, according to the standard model of particle physics, when a beauty quark decays, it is influenced by a force known as the weak force and transforms into lighter particles called leptons. The expected outcome is an equal chance of turning into one of 2 types of leptons, either an electron or a muon. However, the recent findings from the LHC have shown something unexpected. The data indicates that when beauty quarks decay, they are turning into muons about 70% of the time, rather than splitting the chances evenly between muons and electrons. This significant deviation from the expected 50-50 split suggests that something unusual is happening, something that the current theories in physics can't fully explain. This anomaly has sparked intense interest and debate among physicists. The observed disparity suggests that a previously unknown particle could be influencing the decay process, or perhaps it points to a new kind of physical phenomenon entirely. Such a discovery would be groundbreaking, indicating that our current understanding of the fundamental forces and particles might need revising. Researchers are now probing deeper into this data, looking to confirm these findings and fully understand the implications. If this turns out to be true, it could mean the beginning of a new era in physics, with the potential to uncover new forces or particles that could fundamentally alter our understanding of the universe's workings. After a startling discovery, a deeper mystery emerges, suggesting there are forces out there that we've never seen before. Z prime, the particle that will rewrite physics. The discovery of a new force-carrying particle, tentatively named Z prime, could revolutionize our understanding of physics by potentially expanding the current standard model, which is the framework that explains the fundamental forces and particles that make up our universe. This model has been remarkably successful in detailing 3 fundamental forces: electromagnetic, strong, and weak forces. But it doesn't yet account for gravity or explain dark matter, which is thought to make up a significant portion of the universe's mass. The possibility of new physics introduced by Z prime comes from recent observations that didn't align with existing predictions. Such anomalies are not unheard of, given the vast amounts of data generated by experiments like those conducted at the LHC. Still, the specific deviations observed recently have captured the focused interest of the scientific community. These findings suggest the potential existence of a particle that behaves differently than anything we currently understand, interacting in unexpected ways with known particles like electrons and muons. This novel particle could be the key to unlocking many of the universe's long-standing mysteries. For instance, discovering a new fundamental force could shed light on the elusive nature of dark matter and further clarify the role of the Higgs boson in the makeup of the universe. More broadly, it could lead to a more complete and unified theory of physics, which has been a central goal in the field for over a century. The implications of such a discovery are profound, offering answers to complex questions that have puzzled scientists for decades. While the suspected interactions of the Z prime particle with other standard model particles remain largely speculative at this point, the pursuit of understanding it is a thrilling prospect. It represents a potential paradigm shift in physics, akin to the major breakthroughs of the past, but unique in its promise to bridge gaps in our current theories. The excitement in the scientific community is palpable as researchers worldwide work to confirm the existence of Z prime and explore its implications. If confirmed, this discovery would not only redefine our fundamental understanding of particle physics, but also pave the way for new technologies and insights into the very fabric of the universe. Elon Musk has highlighted that CERN constructed the most enormous and powerful particle collider ever seen in human history, known as the Large Hadron Collider. Over a decade, from 1998 to 2008, this monumental project was a collaborative effort involving over 10,000 scientists and hundreds of universities, research institutions, and laboratories from more than 100 countries worldwide. The Large Hadron Collider is strategically positioned within a massive, approximately 16-mile-long tunnel that runs beneath the border area between France and Switzerland, close to Geneva. Buried about 574 feet beneath the Earth's surface, the construction and operation of the LHC marked a significant milestone in the field of particle physics. It first made headlines when it recorded a collision of protons at an unprecedented energy level of 3.5 tera-electron volts, shattering the previous world record by fourfold. Later, enhancements to the collider allowed it to reach even greater energy levels, up to 6.5 tera-electron volts per beam. These advancements have made the LHC particularly adept at handling proton beam collisions and have equipped it to accelerate lead-ion beams as well. The LHC is not just about achieving high energy levels. It plays a crucial role in scientific experiments. Each year, for about 1 month, the collider conducts specialized collisions between protons and lead ions. This period is critical as scientists use it to test various theories of particle physics, examining the data to validate or challenge existing models. One of the primary objectives of these experiments is to investigate the properties of the Higgs boson, a particle integral to the field theory that explains why other fundamental particles have mass. Moreover, these experiments are essential for probing into the existence of a vast array of new particles that theoretical physicists have predicted but not yet observed. This massive and intricate machine at CERN is a cornerstone in the quest to deepen our understanding of the fundamental components of the universe. By smashing particles together at high energies, the LHC allows scientists to peer into the fabric of the universe, offering insights that could potentially answer some of the most profound questions in physics. Today, the work done here is crucial for advancing our knowledge of the universe and could lead to discoveries that redefine our understanding of everything from the smallest particles to the largest cosmic phenomena. With each discovery, we peel back more layers of the universe, moving closer to uncovering the secrets of the Higgs boson. Hadrons are a type of subatomic particle composed of smaller particles known as quarks. These quarks are tightly bound together by a force known as the strong force, which is incredibly powerful and acts somewhat like the electromagnetic force that holds atoms and molecules together. Some common examples of hadrons include protons and neutrons, which are the primary components of atomic nuclei. In addition to these, there are other less familiar hadrons, such as pions and kaons, which were first discovered during cosmic ray experiments in the late 1940s and early 1950s. These discoveries have significantly expanded our understanding of the particle world. The Large Hadron Collider at CERN is a remarkable tool in the study of hadrons. It operates by accelerating two beams of particles in opposite directions to nearly the speed of light and then allowing them to collide. These high-energy collisions create an array of different particles, providing physicists with a unique opportunity to study the fundamental components of matter. One of the most significant particles studied at the LHC is the Higgs boson, which is believed to be a fundamental particle associated with the Higgs field. The Higgs boson is often compared to ripples spreading across a pond surface, as it represents the quantum manifestation of the Higgs field. This field is crucial in physics because it is thought to give particles their mass. The discovery of the Higgs boson was a groundbreaking event in particle physics. It does not carry the properties typical of other quantum particles that mediate forces like the electromagnetic, weak, and strong nuclear forces. Instead, the Higgs boson acts more like a bridge to our understanding of how particles acquire mass. The identification of the Higgs boson at the LHC was a landmark achievement, confirmed through the collaborative efforts of two major experiments, ATLAS and CMS. This discovery was publicly announced on July 4, 2012, marking a significant milestone in the field of particle physics. It validated a key part of the standard model of particle physics, which is the theory that describes the fundamental forces and particles in the universe. This discovery not only deepened our understanding of the structure of matter at the most fundamental level, but also opened new avenues for future research into the origins and composition of the universe. The ongoing studies at the LHC continue to challenge and refine our understanding of the universe, promising even more discoveries in the years to come. At the time the Higgs boson was discovered, it was primarily found in two rare decay channels that provided the purest signal: decay into a pair of photons, which required a totally quantum virtual process, and direct decay into a pair of Z bosons, the carriers of the neutral-weak interaction. Although the finding of the Higgs boson at the time established the standard model, research into this elusive particle did not end there. One of the most significant findings since 2012 was the confirmation of Higgs decay. According to CERN, the research into this elusive particle would deepen during the LHC's third cycle, especially once the particle accelerator's high luminosity upgrade is finished in 2029. This will allow the LHC to undertake more collisions, giving researchers greater opportunity to detect unusual physics, such as occurrences that do not fit into the standard model. CERN estimates that when the accelerator is updated, it will produce 15 million Higgs bosons each year, compared to the LHC's creation of 3 million Higgs bosons in 2017. This might be useful for identifying various flavors of the Higgs boson. Theories that go beyond the standard model of particle physics anticipate up to 5 distinct forms of Higgs bosons, some of which may be created less frequently than the fundamental Higgs. But what's the big deal about the Higgs boson? The Higgs field is incredibly significant and critical in the early times following the universe's creation. It dictates the very nature of the vacuum that exists in our spacetime. It is what causes matter and interactions to exist as we know them, as well as the emergence of mass in all known fundamental particles. Without the Higgs field and consequently the Higgs boson, the cosmos would be devoid of atomic elements, stars, and life. What do you think the Higgs boson is called the God particle? Popular media helped cement the Higgs boson nickname, the God particle, after its discovery. The genesis of the term is commonly traced to Nobel Prize-winning scientist Leon Lederman, who initially referred to the Higgs boson as the goddamn particle, since it was so difficult to detect. According to Business Insider, when Lederman authored a book about the Higgs boson in the 1990s, he wanted the title, The Goddamn Particle, but the publishers disagreed and changed it to The God Particle. That was the beginning of an issue between the particle and religion that continues to concern modern physicists. Nonetheless, it is difficult to overestimate the significance of the Higgs boson and the Higgs field, because only particles would have mass under this aspect of nature. That implies there would be no stars, planets, or humans, which may help explain its bombastic nickname. Aside from the apparent need to accurately characterize the new particle, scientists continue to research the Higgs boson for 2 reasons. First, they want to know how the physical vacuum in which we dwell originated in the early cosmos. Second, they want to know how this physical vacuum can be kept steady following the discovery of the Higgs boson. We dive deeper into the quantum world, where big questions about the universe are waiting for answers, exploring the lost cosmic blueprint.